This work is mainly the work of Paul, actually, who was a really good bachelor student, who was working in our lab for almost 2 years, and is now doing his master's at KTH. However, he cannot be here today, so also I have to give this talk on choosing the right battery model for data center simulations, or more precisely for energy system simulations for data centers. I was actually quite happy to see today that most of the talks, or many of the talks, were not only focusing on carbon intensity, because this was more or less the state of the art in most papers. In the last couple of years, everyone was optimizing for this one metric. And in some way, it makes sense, because probably if we think of future carbon accounting for operational carbon emissions, this will probably be a very relevant metric. However, of course, it oversimplifies a lot of things that are going on in electric grids. So grid congestions, curtailments, and so on are usually not reflected in this metric just because it's too coarse. We are averaging over very large areas, entire countries, for example. So like really local inefficiencies in grids are not reflected here. And this is why also in the last couple of years, we've also seen it here at this workshop, there has been a trend towards better understanding where is my energy actually coming from. So we want to provide computing systems with more visibility and control over the energy system in order to exploit inefficiencies like curtailment periods, for example. So periods where we have excess of renewable energy in our grid that we could make use of to have almost carbon-free computing. However, research in this domain is still really challenging because we're lacking testing environments. So actual hardware environments barely exist. Also, they do not really make sense in many scenarios because they have to be globally distributed. They have to be very flexible. Experiments in carbon-aware computing often need to run over the period of days, weeks, months to really show effect and so on. And this is why earlier this year at the Hot Carbon Workshop, we published a simulator called VESIM, which is a co-simulation testbed where we just plug together some already existing simulators, for example, for renewable energy generation, to mimic the energy system of a computing system. So to mimic an entire microgrid consisting of consumers and producers to test carbon-aware systems. And this thing was in development for 2 years almost at this point, and we keep developing it. You can try it out. It's been used in a couple of projects. I would say it's halfway stable and good, well documented and so on. So we keep working on it, but it's in a good state, I would say. And maybe to quickly explain what we did in this work, I have to explain how VESIM works. As I said, we plug together a bunch of simulators. More precisely, we are currently integrating the System Advisor model, which is a huge bunch of simulators from the National Renewable Energy Laboratory in the US, the Open Energy Modeling frameworks, the different frameworks for simulating renewable energy sources. But also you can plug in your own consumers and producers. So real systems, if you plug them into a power meter and the power meter periodically tells the simulation what you're currently consuming or producing, then this is reflected in the simulation, and the simulation can tell you, okay, if this was a real energy system, then this kilowatt that you're drawing right now would be provided by a solar panel or would be provided by the battery. I'm not going to go into detail of this yellow part here, although this is like the killer feature of VESIM, because you can then again expose all the information that is happening in the simulated microgrid through, for example, a REST API and make it accessible again to real applications. So you can really interact with this energy system simulation as if it was a real energy system. So that was the entire idea behind it. Now in this work, we focus on the energy storage simulator because this was the weak point of VESIM so far. It was very simplified. More precisely, we focus on lithium-ion batteries in this talk because it's just the most common type of short-term energy storage. We compared 3 different types of energy models. The first one is a simple energy model. We call it water tank because this is really how the implementation was so far. You put 5 energy in, you get 5 energy out. It was really all that. Nothing with inefficiencies or whatsoever. We compare this to more complex models. In this paper, in the second here, there was an entire family of models proposed, optimization models with linear quadratic terms. So as I said, it's an entire family. We chose the CLC model because it's been used in related works, for example, in the Carbon Explorer paper by Meta, where they really explore how their data centers should be equipped with solar or batteries and so on. They use this model. And it's short for constant voltage function. It's a linear approximation of the energy content limit. So how does the battery behave when you charge it close to capacity? And a constant discharging efficiency, so inefficiencies. And lastly, we compare these models to like very realistic, low-level physics-based battery models. In particular, the PyBAM model is pretty large simulation suite, pretty well known by now, although it's relatively young, just a couple of years old. And these models really take the electrochemical processes of a battery into account. And second, we use the lithium ion pack framework, which is using PyBAM under the hood, but is not only simulating a single cell, but entire battery pack. And all the battery pack circuit is solved using methods implemented in this Lion pack framework. Since this is a short talk, I'll jump right to the conclusions and the results. As expected, the simple model fails to accurately represent the battery's state of charge, especially when you get in this area of being like at 80, 90% or close to capacity. Batteries just don't behave the same way as if you charge them from 0 to 10% or like somewhere in the middle. So this was not reflected very well. While this CLC model actually did a very good job. So it's state of the art for a reason, I would say. It behaved very similarly to the physics-based models, but it's just super fast. It's super fast because it's super simple. It only contains a linear term. That means it's fast to solve, it's easy to understand. You can even use it in optimization problems because it's really, it's not a complex model. And the physics-based models were a bit of a disappointment. They're behaving actually quite similar to these way more abstract models, but being a lot more computationally expensive, like really in the order of 1 or 2 orders of magnitude. And what's even worse is they're really hard to configure and really hard to analyze. So these models here, you can just you can benchmark your actual energy system, fit a few parameters, and then they behave quite similarly. This one here, you really require knowledge of electrochemical reactions and circuit level dynamics, and even worse, the results of these experiments are very hard to analyze because you cannot simply ask these models for what's my current state of charge. You have to estimate the state of charge based on something, for example, like the output voltage, like you would do it with an actual battery. You probably know that like estimating the best state of charge of real batteries, for example, for your phone is actually a pretty hard job because it depends on a lot of different factors. So that's the conclusion. The CLC model is also now part of VESM. It's available since the latest release. And in the future, we want to experiment more with long-term experiments. So there's this new model, it's called Blast Light by the National Renewable Energy Laboratory. It's for battery lifetime and degradation. And we're currently implementing this one using this battery integration that Paul implemented. And we're also applying this research in systems research. So right now, for example, we're working on a project, on a federated learning project where we use this battery model now to model multiple microgrids, distributed microgrids, and model clients that are powered by battery or maybe even entirely battery constrained. Okay, that was it. Thanks a lot.
Okay, any questions online? I think we don't have any yet, so.
No question from online.
Okay, so any questions from the room? So I have a question basically about VESIM. So what are the capabilities of a simulator like VESIM? So you can couple the grid basically with what's going on in your data center, but what is the end goal? So we can probably simulate different things like where our power comes from, but what about, for example, the sustainability of the batteries themselves or something like that?
So VESM is so far not looking at embodied carbon or something. So, I mean, you can model that yourself, but this is not part of the framework. It's really just about operational carbon emissions. So it really just looks in real time, where is energy coming from, where is energy produced, who is feeding energy to the battery, who is drawing from the grid, how dirty is the grid, all of this you can model. You can plug in your own simulators, you can also plug in your own producers and real hardware and software. But we're only looking at the power system at this point, and not at embodied ambitions.
Thanks.